Yeah, so I'm going to talk about prospectivity mapping. This has started to become popular in the USGS as we're supposed to assess 50 critical minerals in the next 10 years. And so I'll show what I've been working on terrestrially and then lunar application in the Nobili region. Next slide. Next slide. So here's, go back one. Whoops. Back one, there you go. So this is some of the assessment types that we do at the USGS, where we have increase of available information going from bottom to top and increased complexity going from left to right. So on the bottom, we have qualitative assessments, things like mineral inventories, multiple point statistics, and mineral prospectivity mapping. And then as we increase the amount of information we have, we can go into quantitative assessments from the 3-part all the way to 3D modeling. And so today I'm going to primarily talk about mineral prospectivity mapping. Next slide. And so some of the work I've been doing is looking at clastic dominated, they used to be called SEDEX deposits for lead zinc. And so these clastic dominated deposits typically form in rift phases. And so you can see there on the bottom, the package of rocks. This is the rift phase. It's categorized by coarse continental clastics, including conglomerates, red beds, and then this changes into the sag phase. And so the sag phase is categorized by shallow water platform sediments, fine grained black shales, and organic rich siltstones. And so you can see there in red where these CD deposits typically form. Next slide. And so we were asked to create a prospectivity map. And so this is some of the techniques that are out there. On the x-axis, or on the y-axis is knowledge-driven approaches going from poor to good as you increase upward. And on the x-axis is data-driven approaches going from poor good to the right. And so you can see some of these terms that have started being used more as we've gone through this machine learning revolution, things like neural networks, random forests, and weights of evidence. I'm primarily going to be using fuzzy logic techniques, but since we have more data here on Earth, it'll be a hybrid approach. Next slide. And so when you get into fuzzy logic techniques, we have to define memberships. And so on the top left there, you can see this is what we would say is a crisp membership. We've all been to theme parks where they say you have to be this tall to ride the roller coaster. If we look at this graphically, this binary distribution on the top right, you can see that the person on the left has a membership of 0, and the person on the right then has a membership of 1, if we look on the y-axis for degrees of membership. But in reality, we know that there's more than just tall people and short people. There's a distribution like we see in the bottom center. And so if we said we're going to take a distribution of tall people, you can see this log normal curve that we would have all the people who are definitely tall, but then we would be sampling people all the way down to really not very tall at all. Next slide. And so we can apply these fuzzy membership rules to geologic data sets. So these are data sets that I was given to model the classic dominated lead zinc deposits. And so I won't read all these, but you can see there's things like Bouguer gravity, there's deep magnetics, distance to ancient passive margins, satellite gravity, distance to faults, distance to black shales, gravity 30-kilometer upward continuous. Next slide. And so here's an example of how we pull these distributions out. And so the map on the left is the Euclidean distance to ancient passive margins. These are important for CD deposits because they represent that sag phase. And so the yellow squares there are the CD deposits, lead zinc CD deposits distributed over North America. And so if I query the raster in the background and say, what is the value underneath this deposit, I can get that distribution on the left. And so you can see that most of these CD deposits are within about 200 kilometers of an ancient passive margin. But there is a tail on the end of that distribution. And so we want to make sure we also include some of the values all the way out to 400 kilometers. So I can query that raster and produce the map on the right. And so the map on the right is permissive areas in white and light gray, and areas that are excluded in black and dark gray. And so I can take this map and say, okay, anything on this map is permissive. I'm going to add that to my model. Next slide. Here's an example of using aeromagnetic reduced pole. And so I've used the CD deposits to query the aeromag data. And you can see that the values are centered on 0 and go out from plus 400 to minus 400, with the majority of the data being within kind of 100 kilometers positive, or 100, the values of 100 plus or minus. And so I can isolate those in this map. Next slide. And so anything again in white and light gray is included in the model as permissive. Anything in black and dark gray is excluded. Next slide. And we even have some even more complicated distributions. So we have a bimodal distribution when we look at our gravity 30-kilometer upward continuous. And so in this case, we need to do 2 Gaussian extractions on this gravity data. Next slide. And so you can see that the map on the left comes from the data on the left side of the bar chart. The map on the right is the permissive values from the data on the right of the bar chart. And then I can combine these, next slide, to create a comprehensive gravity 30-kilometer upward continuous fuzzy membership map on the right. Next slide. And so going through all those 40 different data sets that I had listed in the previous slide and working through this very process of assigning fuzzy membership, I can then create a prospectivity map of North America. And so what these are used for is for governments and exploration companies then to focus where they're going to spend resources. So in this map, high prospectivity is in warm colors and low prospectivity is in low colors. So this helps focus where efforts should be put going forward. Next map. Okay, so how can we apply this to the moon? We don't have a series of deposits that we know. We can say exactly what the settings are for each map. And so in this case, we have to use complete fuzzy logic. And so fuzzy logic is a completely knowledge-driven approach where we know the controlling factors and we use that knowledge. And so we don't need training points. This is why this is very different than machine learning. Next slide. So Ross Beyer and Oleg Alexandrov have created a 1 meter resolution DEM for the Nobili region of the lunar South Pole. And so from this DEM, Matt Siegler and Jose Martinez Camacho have created an ice stability regions map for this area. And so the darker colors are where ice is stable at the surface. And as the colors get lighter, it's at depth up to 1 meter. Anything that doesn't have any color is considered dry. Next slide. Matt and others have also created this max temperature map, which feeds into his ice stability regions map. And so the bright warm colors have a higher max temperature and the cooler colors have a lower max temperature. Next slide. And then using the 1 meter DEM from Beyer and others, Mark Shirley has created this permanently shadowed regions map for the Nobili region. So now armed with these 3 maps and the DEM, I'm able to create derivative maps, evidence maps that can then feed into the fuzzy logic models. Next slide. So one train of thinking is that the more PSRs you have in one location, the better chance that you'll find volatiles. And so I created a density of permanently shadowed regions map. Next slide. I also created a distance to permanently shadowed regions. And so the thought is as we get closer, there'll be cooler temperatures and more opportunity to find volatiles. Next slide. And then I created a slope map from the DEM. The Viper rover is limited to 15 degrees. And so anything over 15 degrees in red was not included in the model. Anything in orange or green was included, and it was considered somewhere that we could drive the rover. Next slide. I also created an aspect map using the DEM. And so aspect is important depending on where you are on the South Pole. Next slide. And so where we are oriented, the Nobili region, anything to the northeast is going to be considered to get more shadow in the craters. As you can see, like in this diagram, where one side of the crater has more shadows and the other side doesn't. Next slide. And then finally, I created a curvature map, considering that anything that was concave would be more permissive, anything that was convex would be less permissive and excluded. And then I combined all these 7 or 8 evidence layers into a single model. Next slide. And so there was some discussion yesterday about stacked maps and how we can have these stacked maps. And so this is kind of a way we can bring in this data. So this is the final volatile prospectivity map for the Nobili region, with the cool colors in this case being more prospective and the warm colors being less prospective. And so we're using this. What's that?
Going to finish up here.
And so we're using this on the Viper mission. Next slide. And so just to say that, right now with the amount of information we have for the South Pole, we're in this qualitative assessments box, but as we gather more information, the complexity of our assessments will move up to the quantitative and hopefully eventually the 3D modeling and properties population. Next slide, and that's my final point.